Good afternoon, everyone. We all know Bert. He gave a talk not so long ago at ETH, and he accepted the difficult duty to do a tutorial. So he did the first part of the tutorial, and next week will be the other part. We are broadcasted live in many places at the same time because it's a special event of the NCCR Catalysis. And so people that will have questions, they will have to send me something on the chat, and then we try to translate that as much as possible. And without further ado, I will ask Bert to proceed and to show us what we need to know about Operando spectroscopy, the basics. Thanks.
Thank you. Thank you, Christophe. And I think also many thanks for giving the opportunity to do this kind of challenge. So it will be today and next week. So it's part A today, and then part B will follow. It's about a period where I would like to, at some point I will stop, we have a break, and then we continue. So it's around 45 minutes. So I hope at around 6 to make the break. And what I would like to do is to give not a regular talk. Actually, you can also email me. I will end with a question 4, where you're even engaged to send me an email, where you have to think about something. And what I would like to do is to give a kind of background on what this field is all about and how you maybe can also have it used in your own research. I'd like to start with an image I like. I'm a Belgian, and that means that I like certain detectives or trying to solve murder mystery games. So in Catalysis, we want to know who done it. And it means that we want to provide insight in the active site, in the reaction mechanism, the activation phenomena, and the effects of support, or in homogeneous catalysis, the ligands, the surroundings, promoters, solvent effects, and so on. And that means you have to develop and use methods. You can use theoretical methods. That's not my hobby, but I'm one who tries to use experimental approaches. Now, another thing is, whodunit in catalysis is a quote which also is known to you, is seeing is believing. And here I put a lot of books, and what we have is all what I call textbook chemistry. I'm not saying that the textbooks are wrong, but we always have to challenge everything that is written, because that's the way science progresses. So we have to dare, and I will show you in part B an example, not today, that we have to dare to question what is in the books, and that we have to interrogate our catalytic system with methods, theory, or experiment to get that done. And that brings me to the lecture of today, tutorial. I'd like to talk about Operando catalyst spectroscopy and its need. Then I will talk about some history. Then I present you a social network, because we are all scientists and are connected. Then I will deduce from that social network trends. Then I will focus on, and I think that will be for many of you very interesting, practical aspects, where I will focus on cell design, and also on the quote, measure is perturbing, where I will show you that is by no means you can be sure that what you do is not inducing something else. So you have to double check on that. And I will end with a showcase, if I allow, otherwise I skip that for today and I will bring it for next week, is closing the process gap. And I will give you an example where actually we bring it Operando approach to the level of a pilot scale reactor. So I start. Operando catalyst spectroscopy, of Operando spectroscopy. There are many catalyst characterization methods. And here I show you some books. I'm quite sure you know many of these books. One of them is known as Hans Niemansverried from the Netherlands, actually from Eindhoven University of Technology, just retired. But he has been one of the persons who have been pushing, but also writing textbooks on spectroscopy and catalysis. There are many edited volumes, but also luckily there are also chemical society reviews, chemical reviews, many thematic review papers of issues where you can find a lot of information. When I focus on the book of Hans Niemannsverdiet, I think that many have maybe remember a figure which is you can find in the early pages, which he calls the hexagonal for catalyst characterization. So we have toolbox that's actually at home. I'm not that good in that, as you can see, but okay. But we want to develop a characterization toolbox for catalysis, for spectroscopy in catalysis. So there are many possibilities. You can have photons, ions, electrons, whatever. Today I will focus, and also I think mainly next week, on photons. Most probably I will introduce next week something on neutrons as well. When we think about photons, and now it's very basic, I think you know this scheme and the electromagnetic radiation, the electric field, magnetic field, and it's a wave. And the wave has wavelength, and means also that there is energy associated with the photons. Now you have different energies, hence you can have in different ranges of the electromagnetic spectrum, you can have interaction with matter. And that is what we actually are doing. We use, for example, infrared or microwaves or X-rays or lasers, and then we introduce the interaction with matter, the catalyst, and learn from it. Which brings me to my first question to you. So which techniques are you using in your work currently? So I'm just pointing out to you, which technique are you using in catalyst characterization, or you do not characterize your catalyst? That is also possible. So in your case, EPR. Who else wants to raise his or her hand? EPR, then there should be one with NMR, no? TERS, but that was not a very surprising one because I know you, Naresh. So tip and hand straddle, or in the category Raman, we will call it. Someone else? So what you can do is actually
ETQT, I have from the chat line.
Good. So maybe you're surprised, and I must say this Web of Science, it's always a bit tricky in the sense that you have what keywords you put into the system. But I just show you here what I did actually yesterday. I found what you find is actually a lot of NMR, but I think that has to do with the use of NMR to identify your molecules, not per se for the catalyst. A lot of infrared Raman vibrational techniques, I think. And if you see certain things are a bit rare, EPR, it's really for the specialist. Mersbauer is completely, I would say, and it's limited to, as you most probably know, a lot of iron. And even synchrotron, although you have here your own synchrotron, is rather limited. And that's most probably because you need a lot of expertise to go to a synchrotron to get something done there. And you have to have a beam time application. So I come back to this because I will end with question 4. I will already ask you. Then I will ask you and propose to you is design for me an Operando in situ cell or Operando in situ cell which works properly with 2 techniques you're using in your work. So then you know already what the question will be for, but we build up towards this question. So there are many books, and this is a book I once had, but there's also one from Jim Howe and many of them. And that's all fine, but there's another book which maybe you're less familiar with, which is catalysis from A to Z, and that is a kind of encyclopedia. Then you can start to find words, and it's very funny actually. You can find Operando spectroscopy or Operando methodology. I will come to these references again, But what is it all about? It's spectroscopy of the operating system, the operating catalyst. And it has a history, I will explain later on. So many people are used to the word in situ, Latin, at its place. So it's actually, that should in principle be at its place, at its working place, but that is not always the case. Secondly, the word in situ is often even used for what I call fossilization of your sample. That means that you have your sample and you have it at a high temperature and then you quench it. For example, there are several NMR studies where they use a quenching method. They bring it down to low temperature and then measure it. Especially for magnetic techniques like EPR, magnetic resonance technique like EPR and NMR, where the temperature really matters due to the Boltzmann distribution for measuring spins, nuclear spin and electron spins, you need low temperature, and therefore they use fossilization methods. Real reaction conditions, what does that mean? High temperature in a gas stream, in a liquid. And that brings me to a kind of quote: conditions are often a compromise, because back to Boltzmann distribution, actually you have to have a difference in spectroscopy between the lowest level and the highest level. And that means that it is temperature dependent. And when do you have the best spectra? When you have a lot of here in the lower level. And it means that you have to bring it down to low temperature to have good spectra, which is in contrast to often reactions where temperature is needed. So it's somehow a contradiction in terms. There are alternative names for this field, and that people have been proposed, and you can find it also actually in life sciences, in vivo spectroscopy. But after some time, the word Operando spectroscopy as a subset for in situ spectroscopy emerged. Now, I have already my age. So during my PhD, it's actually this one of my master students. And in my PhD time, what we did is we did not have so much of these fancy in situ operando techniques. We did fossilization. What I mean by it is we had these cells, we actually filled there as one, and this one belongs to each other. Actually, we had their powder that was brought into a reactor where we were flowing gases through. And it meant actually that you can bring it in a reactor, heat it up, having gases over it, but you had actually always to remove it from your furnace to get then this window put in front of a spectrometer. You can also, for example, pull vacuum, that is also possible, and then do things. But what you had was conditions where you first do a reaction and then you analyze. And here you can see this gentleman. This is this window here is for UV-vis measurements, and this actually is an EPR tube you can put in a reactor, and you can do combined, and that was already advanced in these days. I talk about the 1990s, that you can do combined UV-vis EPR of the same sample, treated under the same conditions, but of course, totally not under reaction conditions. Here I show it in a different way. Here I show you actually pictures which I've been taking, they come literally from my PhD actually. You can see here spectra, and yeah, in this case it's a chrome alumina catalyst. No details about this now, but what you see is that you can calcine it, activate it, reduce it. Then you have it after reaction, RIP, rest in peace. And then the question mark is there where, and that was what it was. So in 2002, I wrote this invited paper for Chemcom, It was related to the European Conference on Catalysis, where I had an invited talk, a keynote lecture, and I was a young professor. And in these days, actually, we felt as young scientists that this whole in situ, whatever, that was not the way to go. I was not alone. Actually, there's another one. It's Miguel Banyares. He's working in Madrid. And here you can right away see the title, Operando methodology, combination of in situ and simultaneous activity measurements under catalytic reaction conditions. At the end of my talk today, I actually will show that, in my opinion, that definition needs to be reconsidered because it's not sufficient. Because in my opinion, operando means that we really try to push it in such a way that it really tells us something of the operating system. And then it's not enough to get knowledge about just that you online measure it. Because I will explain in a minute that it means you have to go in a kinetically relevant regime to get relevant information out of the system. So we have, as others, been developing this idea of operando spectroscopy. On the left, you can see a schematic. So what you have, reactant reaction products, you analyze it, and you have literally shining light into the reactor and hopefully also shining light on your reaction mechanism. On the right, you see an image of a reactor, which actually is at Utrecht University, where we combine X-ray diffraction with Raman. What you notice that there are many combinations of techniques from various groups where they try to combine methods. Here's another one from our lab where we use actually UV vis on the left, Raman, the green laser on the right, and the reactor. And actually here inside, you see actually a broken part of this furnace, but you can actually, you drill holes in a reactor. So you bring the spectrometer to a normal reactor where you can analyze. So one could then say, that's easy. So we make the operando spectroscopy dream machine. So here you see the dream machine. What it could be is actually a kind of animal with everything, where it provides you an egg, hopefully a useful egg, that's not sure yet. But what you want to do is you want to ask yourself, am I now building a reactor system, or am I interrogating the system to learn from? And that is an interesting quote, because at the end of the day, we want actually to make sure that we learn and that we get new insights. Now, there is a reason why you combine methods. And I think it's fair to say that almost none of the catalytic systems I know are as simple that with one technique you can solve all your questions. So the question is then, where do we go? And I hope that I can show you later on that there are directions to go. Now, the last sentence I would like to put, because choosing the right reaction system for an operando setup, are we making the setup to solve a reaction, or are we thinking of a reaction to be put in our system? I think we have to be always having this scientific question in mind. One of the systems we have been developing about 10 years ago, and I think that is something what you see now also at synchrotrons, is that very complex systems where you combine, and here on the right top you see a reactor, with an orange powder with a catalyst. You see the heater guns. Now this is a very interesting one. So you have heating guns around a reactor, a capillary, and you have a lot of space. A lot of space is good because it means you can start to put a lot of techniques which can be wide angle X-ray scattering, X-ray diffraction, you name it. And just to show you here it in practice, here you see it better, the right photo, you see this, you can put UV vis or whatever, but what is here an issue, and I will come later on with it. What is the issue? You have heating guns. Now, the heating gun is maybe in the actual direction still doing a good job, but on the side, it's a leak of heat. So what I want to say with it is that you actually are not mimicking the reactor well of your lab, because there is just dissipation of heat. Hence, you have gradients across this reactor. On the other hand, it is very elegant because you can, of course, have a lot of space to do that. Now, this whole challenge in catalysis, where you try to push the system to the level that it becomes interesting, real catalyst, real reaction conditions, this field of in situ operando. So actually you're bridging the pressure or temperature gap, bridging the materials gap. That remains until today a challenge. Are we going to the most complex system and the most realistic conditions, but we give in on information? Or are we going into model systems? And both actually have their merits. And that is shown actually here in this slide, where you really show this materials gap going from single crystals, supported nanoparticles, or the mesoporous materials. And I'm quite sure that Naresh will agree that with industrial catalysts, it will be not easy to use tip-enhanced Raman spectroscopy, because your surface flatness will avoid that you can have good samples measured with this technique. So it shows that a lot of STM, AFM, and whatever methods will not be so applicable to the right type of catalyst and very well for the left. On the other hand, with techniques like synchrotron methods, I think you can do a lot of interesting studies on catalysts. What we forget is, and that is another complication, is catalysis is not always, organocatalysis is an exception, because then there is carbon or whatever, but it's often organic, inorganic chemistry thing. Also in homogeneous catalysis. So you have a metal complex with ligands and organic molecule. And it means that you have often high Z with a low Z element. And there starts to be an issue, because techniques are not always susceptible or amenable towards the low Z or the high Z. So you will have to make sure that you're able to measure both at the same time if you want to understand catalysis. So that brings me to my second question, and here you don't have to answer, but I'm just interested, and I hope you can raise your hands. I'm interested is how many people are here in the field of homogeneous catalysis, heterogeneous catalysis, biocatalysis. So let's start with heterogeneous catalysis. For those who are online following, a lot. So homogeneous catalysis, it's less. Biocatalysis, I think I'm less attractive for the people from biocatalysis, that's clear. But that's fine, because I'm also not so working much in biocatalysis. But just to say is that I will show you one example of homogeneous catalysis, although maybe not in the best conditions. Later on, I will show you an example, but I will for next week also make one example from homogeneous catalysis to make sure that you also are served or learn something. Now I would like to show you a slide which I have been showing before. And I do it for one reason, because whodunit catalysis was the active site. And for those who have been following previous talk, they know that I like history. I also like photography, and both helps me actually in my scientific work. And that means that Taylor was talking about the active site, and he thinks it's a defect site, but that Taylor was very influential. And now I bring you back, and I really will read it, because I will bring you back to 100 years ago. 100 years ago, Taylor wrote in Nature. It was not yet a popular journal as it was now. I have to say, people were not knowing impact factors or whatever. But I want to say this, Taylor, he wrote, perhaps, so the right column, for those who are following it online, Perhaps, however, an illustration involving the application of the research of the brilliant French chemist, that's his appreciation, Paul Sabatier, will serve to demonstrate potentialities and possibilities inherent in academic research. And how it comes. Sabatier is a discoverer of the principle of catalytic hydrogenation and has conducted an exhaustive series of researches into this phenomenon. The application of his results to industry has solved the century-old problem of the economic utilization of liquid fats. During the last 10 years, and in ever-increasing measure, liquid fats and oils have been catalytically hydrogenated in the present reduced nickel as a catalyst to yield the more valuable hardened fats which are used in soap and candle industry, as well as the purpose of food. And now comes the very one. The economic results of such application are tremendous. Whole tracts of tropical country are being opened up for the production of palm nut and other nut oils. You cannot imagine that. You would never write that down now. You agree? And then comes fish oils are being hardened and deodorized for use in industry. New uses are being found for hardened cottonseed, linseed, and whatever. And then, interesting, although it was at that moment not so popular, catalytic hydrogenation has also been applied for the enrichment of gaseous fuels. The carbon monoxide of water gas may be hydrogenated in the presence of reduced nickel to give methane and so forth. Methanation reaction. So you see how times change, times evolves. People write in famous journals, whatever. But the time also shows that things can change and things change. I will now show you this reduced nickel in this reactor, this reduced nickel. And this is cottonseed oils, rapeseed oil. This is rapeseed, and if you take the rapeseed out of it and you get this oil, then you have to get rid of the glycerol, actually. You can actually start to harden, and here you make stearine, for example. It's done in large reactors, these kind of large reactors. And I have actually a movie to illustrate what is happening. And then I will, so I show you this movie. That is what we write down in the textbooks. And the question is, how we should. So here it's a liquid. The catalyst will hopefully show up. Yeah, there is the catalyst particle. I hope it, yeah, here is zoom in. The metal nanoparticles of nickel are these blocks. There you see an olefin, the fatty acid molecule, and you see that it is hydrogenated. And here you note it further. So we go to another nickel nanoparticle. There lands again the double bond. Again, hydrogen comes. But one of the reactions you cannot have as a side reaction is that the hydrogen is added, actually isomerize it. And then the hydrogen is going back. And then you have trans fat, which is not wanted in food applications, for your information. How do you know this? Well, you can write it down or you can measure it. And that means you can use this kind of liquid phase ATR infrared reactions, which makes that possible. Today, I just introduce it. Next week, I show you an example of biomass conversion. Back to the history. Now, spectroscopy has been around since long. Spectroscopy in catalysis has been around since long as well. Something in the 1940s, 50s, you see publications. I will show you right away two of them, which in my opinion are one of the first applications in the field of infrared catalysis. Then you see that it goes further and you see your EPR technique popping up, and Meusbau and several other techniques are used. Now, the first paper, to my best knowledge, has been from Huygens, where he is using infrared, and he is using ammonia and CO sorption. That are the first papers. And what they are doing is they analyze the catalytic activity, and separately they analyze CO and ammonia. And let's be fair, we still do that. True? That's still what we do. So Huygens somehow has set a scene for years when we are using this. Then in such a search, we found a very interesting paper. And this is, and you can challenge me because I'm looking forward. Email me if you found an earlier one. To my best knowledge, is the first, which we would call now Operando. On the right, you see the catalyst crystal. It actually is a copper crystal. And the fun thing is they have actually electrical circuit because they measure also the conductivity of it. A crystal conductivity. Very funny, actually. I was surprised to see it. Okay. Then you have a furnace, gases in, actually you mix them. This is a propylene oxidation reaction. So you see propylene and oxygen and helium flow meters that comes into this cell. Then you go to the vent and there you have a gas chromatograph to analyze it. So this is purely Operando spectroscopy, but it's not named. So you see that the ID where you link activity, performance, catalytic performance with spectroscopy has been out for a while. So since then, this field has been developing, people have been pushing, trying, etc. And in 2000, and I already mentioned that, in several young scientists around 2000, I still call myself young, but also others. And we felt that the word in situ was almost always used for words which were more of work which was more linked to fossilization, to things where it was not clear yet if it was really catalysis what was going on. Interesting studies, but what was the connection to catalysis? And my postdoc advisor, Jack Lunsford, actually, when I gave my talk on my PhD, in that moment, I don't know what the transition here is at ETH, but when you start as a newcomer in a group, then you, as a postdoc, then you give a presentation on your PhD work, and then you get comments. And one of the comments I got from Jack Lunsford, my postdoc advisor, was, Bert, what is the connection to catalysis with your beautiful spectroscopy work? Yeah, I understand that you're now able to quantify chrome 2, chrome 3, and whatever, but what is the link between the chrome 2 and 3 and the catalysis? In that question, and therefore I hope that when a supervisor will tell you some of these nowadays other questions to you, that it make you think, because for me it was actually confronting, as it was to other scientists as well. So in 2000, a group of young scientists came together and they felt at this conference here in Washington, DC, we want to do something different. We have to make it clear that it's something else. We also decided to launch a conference, and I was the first one who had a tenured position. So because of the risk to organize a conference, I was then the chairman. That was the idea. So here you see the paper of Banyares, myself. In 2003, in Lunteren, a small place in the Netherlands, we organized the first Operando. There was a lot of people who were responding in the positive and the negative sense, because people were saying why we need to know name. And therefore you can also see here that we had this Operando conference proceedings published in PCP. And one of the articles which I wrote as a preface was, Operando is more than a buzzword. It's more than a word just for the name, because I feel that we should try to connect spectroscopy to real life catalysis. For those who were there, I don't know if they are online, but I put here a picture of Jeroen van Bokko on the left, Monique Tromp, Simon Baer, Angelica Bruckner, Jan Dirk Grunwald. That's me, still with more hair. Yeah, I think there are more people, but that is what I now recognize. So since then, there has been a tradition. After Lunteren came Toledo. Miquel Banyares is a Spanish one, so he chose Toledo. Rostock, that was Angelica Bruckner. Brookhaven was, I think at that moment, was Simon Baer there. Deauville was Marco Dauturi and the group. Nestopane was the first author on the paper. I forgot actually to mention. Gueres Perez was working there. And next year, I hope, and it's a tutorial which Martin Nachtigall already gave when he gave here a talk in Zurich, and David Ferry, they will organize it here in Switzerland, which is Grindelwald. I'm sure it will be a beautiful place. Now I want to introduce something which you think like, what the heck is this? A social network. But I will explain you in a minute. I like it very much, therefore I show it. Not that it is fully true in the sense that, but it allows you to make links between scientists. And science is, as you maybe not know, is done by you people, and they make their own career, and you see the sons and daughters or whatever, and yet actually you see family trees and people interacting. And that holds also for Operando. So the first thing I want to show you is when you analyze the literature data, and I have to say, I did it for the last Operando conference in Spain. So this is work from 2018. I did not make an update, but the trend of the way of what it is still true. So here you see the different conferences, and you see the number of papers increasing with time. Then you can note actually that you can also put a lot of keywords related to it. And you will note actually that the Operando term is spreading out of where it first started, heterogeneous catalysis and homogeneous catalysis, but now spreads out to battery sciences, life sciences, whatever. They use also the word in Operando and other variants of it, but we use Operando. I just have a few examples of what I call a bit different type of papers. Development of Operando protein film infrared electrochemistry, completely something different. So that reminds you of this in vivo spectroscopy of catalyst systems. And here you see another one, which is Operando electron nanotomography, which you think in the microscopy world, although it has been difficult. And next week I will show you an example of Operando electron microscopy. That means online. But back to this social network. So what is the whole idea? And it starts with key papers. That's very subjective. But I will show you how I came up to these key papers. So we took about 50 key papers. And what you then can do is you take, computer takes, not me, takes all the reference lists. And what you do is you do actually forward and backward in these references. So you have a paper with a lot of, and then you link it to the other paper, to the other paper, to the other paper. If you do that, you get this. I hope it will work. Sorry. Where is my, here's my cursor. So I hope it works. Yeah. So here you see, galaxy of a lot of papers. You start with the papers and then you connect them. When you see a connection, that means that the papers are linked or the authors are linked. And now I zoom in. Because, yeah, okay, my name is there. You see also, so that it is in the center, that has nothing to do. That's just an artificial thing. The whole point is what I will now zoom in is on clusters. You see what I mean is you see that clusters on the left, on the right, and whatever. And that are groups of people using similar techniques. So here I show you actually Bell-Nielsen-Norskov cluster. Actually, this is all the field on the where you saw the electrocatalysis, the solar fuels appearing. Alexis Bell, for example, had one of the first papers where he has been using this in the field. Then you hear this is a lot of tomography work, and so no, this is battery work. Excuse. Then here it's a lot of X-ray work, synchrotron work. You see here Frank de Groot and Andrews. Here you see Grunwald. See a lot of techniques which are synchrotron related. And what you can now do is you can, here you see Biker Urakawa, some of them you know, Newton Ferry. And here you see what I call the Raman spectroscopy, Banyares, Mestel, wax. And now you think, okay, what I can learn from it, but you see that actually it groups and people, and that is, we do that almost all of us, we cite each other, and then they start to group, and the closer they are, the more you cite to each other. That is actually the message of this. So you can see here that you can have in these, for example, Topse and Clausen. There's also X-ray, but it's a lot in older work actually as well. And here you see the Chen Hofkens Roofvars, that's single molecule spectroscopy. And here I show them all. Of course, it's very personal because it depends on these 50 or 40, whatever papers you start with, because I select other papers. But on the other hand, what you notice is that there is also something, because papers which are many times cited, they will right away pop up in all these reference lists anyway. So after a while, I mean, there is a relationship when you have this. Now, you can ask now why you do this. You do that not for these authors and the social network, interesting, but you want actually to know trends, because it provides you also not only the reference list, it provides also keywords and main topics. So I could make a cloud, a word cloud. I did not do that. But here I show you that we had another approach. We asked many people, some of them you know, and we asked them for the most influential papers in the field. That are those. I will not dwell on them. Also, this is personal, but it somehow overlaps with the analysis we did. It's not that far away. What do we learn from it? We see a lot of combining methods, better operando cell, single particle spectroscopy, and more the right, a lot of electro, photoelectro, etc. Biomass, although it's a bit fading, but now you see a lot of polymer waste, municipal waste conversion, etc. And an example, which I will show next week, will be on liquid phase. Another thing what you will notice is that operando spectroscopy goes nano. More and more you see single atom, single molecule, single whatever, single particle, a lot of this single analysis. And this is due to methodologies where AFM is combined with methodologies with spectroscopy, which allows you, and there is it pushed. And the other thing is you see more and more electron microscopy, which allows you, and X-ray microscopy. And it leads to, back to this Operando dream machine, where people try to have different tools into the system. But that's not the only thing. The other thing what you notice is that we want to measure longer and more in transient. We actually want to follow the life of a catalyst. At synchrotrons, people are now more and more arguing, can we have longer beam time periods? Or even, can we have our setup there installed for a while, and now and then we take our sample and analyze it, but we keep it running so that we could, in principle, really ideally, follow your catalyst system for 3 years. It's a dream experiment, but that would be fantastic. The other thing what you see is that you bring spectroscopy to the lab, or also X-rays, and you want to measure long time at your lab yourself. And that is because, as I will show you next week, and for those who followed some of the talk which I gave previously here or at EPFL, they know that I argue that a catalyst is formed in the reactor. You make a material that is there, that baby has to grow, and what you often see, and people in industry will confirm that, for large industrial operation, you see actually that the system has to develop itself a bit. And once it is happy and well, it behaves a bit like the one here on the left with its thumb up, where you feel the thing is working well, and then hopefully you can delay the deactivation, the RIP phase, for as long as possible. but you want to follow this genesis of the active phase and the deactivation of the active phase. And that makes that we will harvest a lot of data. And it means that you will have to start to think about this AI, whatever all, because it's not very popular, but I would call it data management, data handling. And for example, some of our coworkers, from my coworkers, when they go to a synchrotron and they have X-ray microscopy data, then it's hardly to put on a disk. It's not so easy anymore to put everything on a transfer disk and hard disk to go from a place, Hamburg or whatever, synchrotron to Utrecht, because of the management of this huge amount of data. And then you have to analyze it. And often you're working longer on the data analysis than on the data measurement. Now we have covered 6. So I propose that we have 10 minutes break and then we continue. And then we will continue at, I think, a very interesting piece, which is cell design and measuring is perturbing. So see you over 10 at 6:10 we restart. Bullet point 5 and 6. As I already mentioned, I hope I have time to discuss them both. But if not, then I will leave time for 6 next week. But I think that I'm rather on track. So I don't know if it's now time. It's okay. Then we start further. I don't know. Understood that there are several people online. I think it's very nice to email the questions to Christophe, and then he will then also take care of it. So I would like to talk about the practical aspects. Cell design and measuring is perturbing. And today I will hint on several things, and next week I will then come back to it and just say, well, for example, here, not a good gas hourly space velocity, or things where you can say, well, the relationship with catalysis is not strong enough or could be improved. So cell design, here you see 2 of my former PhD students holding a cell. This cell is used, for example, doing infrared spectroscopy, where you can bring it under high pressure. For example, the right one is Charlotte Vogt, who has been doing the CO2 hydrogenation work, which I already showed you previously. When we talk about such a cell, then we have to consider several aspects. Well, first you have to construct it. And I always joke, but it's so important for PhDs and postdocs to realize that you're so dependent often on the machine shop of the people from the instrumentation division. I don't know what you have in your own university, that you have to make sure that you treat them well, and that you sometimes bring a cake or whatever to them to make sure that you're, because it's far from trivial to build cells. When I show you this kind of cell, you can buy these things, but you can also build things. And often you will have to, you buy things, but you modify it, or you start to buy it and you build later on your own thing based on the design, and you found out all what was less good in the cell you bought. Or you go in contact with the people who deliver a cell and manufacture them and do it together. And that holds certainly for when you work together with synchrotron radiation sources, where you go to beam lines. You have aspects which are related to the catalyst material and aspects related with the cell. The mode of measuring electromagnetic radiation determines it all. Is it transmission? Is it fluorescence? What is it? When it's transmission, it means you have to consider your energy because you have to get it through. You agree? So your thickness of your pallet matters, and also your absorption properties for a certain wavelength. The catalyst temperature, where do you measure it? Is the temperature, or is it lower? I can bet that most of the cases, the temperature is wrong, unfortunately. The catalyst form. You saw in this first example, which I showed from 1969, that there was a crystal. What I mean is you can measure a crystal, but you can also press a wafer. If you press a wafer, that's very interesting. Do you have diffusion limitation after pressing it with so many tons on the pallet? I will share you right away something when I did experiments. I will show you later on the cell that I have been making wafers. I put it on a holder, and the gas was flowing over it. And on the front end, the color changed. Read, hopefully, reaction. You turn the pallet, just the fresh powder as you know it. Hence, your front thing has been reacting, the back, nothing, or hardly. Catalyst damage, measuring is perturbing. Aspects related to the cell activity. Are you really measuring operando conditions? Are you really having activity? But here I mean something else. Is the cell itself active? Because the cell is made out of metals or whatever. Assume you do metal-based catalysis, it could be that your cell is reacting, especially when you have corroding conditions that you are start to expose the metals to your gases or whatever. Cell volume. Is a cell volume big? That volume means no transient experimentation possible, and related to it, what is your, and I refer to this gas hourly or liquids or this true going through the system, what is your conversion actually? Do you really have conversion, or do you have just gases or liquids somewhere sitting in the back of the reactor, and because there's bad mixing, it stays there? Spectroscopic window. Yeah, you need, of course, for every technique, a certain window to get something through. But it means if you combine methods, then it's not so trivial, because what is in the window? I start with a cell or two cells from my own time when I was a postdoc. So this one here comes actually from Israel Wax group. There you see the cell on the left, the picture. You see actually the laser light, green, coming from the bottom, going through this objective in the middle. And okay, the gases are not now connected, the gas connection, but I hope the ID you see, and here it is shown on the right. What is it? It's a shaft. You make a wafer, you add it to the top, the shaft turns. It's a reason for that it turns, because it's actually a bit offset from the middle, the center. Why? To have making the laser having a rotation, or having the sample rotation, so the laser is not hitting always the same spot. If you would have always the same spot, you have laser-induced changes. But I hope you also see that here this cell has a large volume, and you can also see is the thermocouple is far from the sample. You see? So is this the way? Another one. Oh, sorry. This is a paper just to show you that you can do that, but that is, you see, in situ Raman spectroscopy of supported carbon oxide reactivity studies with methanol and butane. Okay. So methanol and butane have been going through that system. Another postdoc, I was with Lunsford, then this was a cell. And here you see in the middle, you see the catalyst bed. The thermocouple is just underneath the catalyst now. And then you have here these, on the left, you see this spirals, it's actually the heating coil. You can put that on, and so these two have to be combined. And a laser light can hit the sample, and you go through the system, because this is gas flow in, gas flow out. So now I have my third question to you. I already hinted on certain things, but now I invite you to make comments on these two cells. So I go to you because I know you already. So I was just wondering, what do you think about the top cell? What are, in your opinion, the pluses and the minuses of this cell?
The obvious negative is that the temperature is not right reactive when it's not in situ.
So the temperature is not right, maybe, yeah. Next one.
Also, the red volume is pretty high. So
Pretty high, I would say very high. The dead volume is very high. Next one.
Means that you can't go for high pressure application if you have to, for example.
Yeah, but I think it was made out of quartz. I think you blow it up. That's something else.
Okay.
But we didn't try it, I have to say. Next.
Also, the gas flow is so if you have to mimic a reactor, for example, the gas flow is completely different compared to an actual reactor.
Yeah, it's completely, it has no resemblance of an industrial reactor. I think that's true.
Whereas the second one, although it's not.
But I also want to have positive things about this. I mean, it's all fine to have negative things, but I also want to have positive. We could publish it, and there are many papers with this cell published, so it cannot be crappy. True? I mean, yeah, I don't know if it's true, but at least in these days we could publish it. Let's put it that way. So what are the positives? It seems for those who have followed it online, he has problems to formulate positive things about this cell. I should help you. Yes. Well, the first is I already hinted on this shaft which is rotating, is that the beam damage can be diminished when you rotate it with the right speed. Second is that you have a nice wafer where you have, if you have your optics right, after these days we have to measure for a while, but you can measure beautiful spectrum. It's actually, the cell is really from a spectroscopic point designed, but not from a catalytic point of view. See? And then the bottom one, now I give the hint, of course, because the bottom one is then
It's shaped more like a reactor, so it
Yeah,
gives you the advantage.
it's a tube.
Yeah, it gives you the advantage that you're sort of dealing with more similar conditions as a reactor.
Mm-hmm.
But then the downside would be you don't get the similar, for example, you're in the prior case you're getting you can apply it for reflectance, for example, but this one, not sure how you use it for that.
No, it's actually, you measure the light beam, so it's in 180 degrees mode measured. So you measure it, and then light is going back. But what one of the things is, you see the gas flow is going from left to right, and it is because on the frit you have actually granules of your. It's not a pallet, but now you have granules. And I can tell you that if you are not careful and there is some back pressure or whatever, then your powder flows out of this holder, and then you can restart to do your experiment and things like that. So there you see the disadvantage of it. But the good thing is the thermocouple is underneath, so that's the positive thing. But the light beam will always hit the same spot. Hence, you will have also effects. When this cell has been compared, actually, this cell has been compared with lab, the bottom one with lab activities. And there you can note actually that also the temperature is not correct. The temperature is because you are heating much more the sample. You also can be a bit off, 10, 20 degrees C can be off. And that is something what you have to be careful in always these designs, that what is the temperature? In the top one, actually the thermocouple does not tell a lot. I think we should be careful on that. Now, I want to show you, I hinted on heating effects. And I want to show you a reactor which we have been developing, and it is on the left UV vis, on the right, you see optical fiber, no, sorry, a Raman objective. And this is a system where you measure UV vis and Raman, I'm not saying on the same spot, but on the same, a bit on the same catalyst. Now we have been doing something with an infrared camera. You can use an infrared camera to follow the heat. You agree? So with an infrared camera, we have been measuring the heat, and there on the top, you see the increase when the laser is on or off. Of course, this is now a certain experiment has to do with the flow rate and whatever. So I've now been, it's not so important what the value is. I only show with an infrared detector, you can actually measure the heat increase. It's there. How can we also detect that? Well, another thing is the spot is very important. Here I show you A, B, C. Now the A, B, C is there where the laser hits. B, you move out. And then you see the UV vis. Now that's interesting. You have two techniques. One, the UV vis have actually a broader thing than the laser. And you measure the effect it has on the UV vis spectrum. And what you notice is that the temperature increase when you reduce chromium-6 to chromium-3 is actually enhanced when you are having the laser on. Because the laser increases the temperature, hence the reduction will be more easy to go. So here I show you the offset between Raman on, and you see actually how easy the chromium-6 reduces because you put extra temperature in it compared to UV vis. So two techniques, you use a second technique to check the first technique, you can say. It's very important to do that. I would even say, and now I give you another example. The first attempts we did in, people know that I'm working on propane dehydrogenation, the first attempt in situ spectroscopy published in whatever journal, we have been measuring conversions which are different from what you have in a normal reactor due to what you have on the system, because the temperature is not right. And with an endothermic reaction as propane dehydrogenation or an alkane dehydrogenation, it matters, because if you have at 550 degrees 40–50% conversion, and you can increase a little bit the temperature and you get at another 20 degrees, then you shift the thermodynamics towards higher conversion. Hence, be careful. Hence, double check with the normal reactor. I promised you an example, homogeneous catalysis for beam damage. So I showed you temperature effects, and I hope you now understand that it's so important to put the thermocouple or a second technique to evaluate your system. Here I show you experiments which we actually did because a professor from Delft University approached us, and he was active in copper complexes. It's an alcohol oxidation to benzaldehyde. I'm not a specialist in it, tempo, copper phenanthroline. What I want to show you is on the left, you see the UV vis. There's a combined setup, UV vis, X-ray absorption. So if you would see these results, you say, yes, left, I see changes in the spectra, right, I see changes. I'm doing interesting stuff. That's what you do. Now I show you X-ray beam on for the UV vis, X-ray beam off for the UV vis. Do you see? So on, nice bands formed. You think, yes. Off, the UV vis is, I'm not saying there's nothing happening, but it is definitely slower. So I hope that if you would not have the capability, so assume you did not have this technique, and you would only have this, and you would say, I will base my paper on this data, then you will start to say, oh, I have a reduced copper and blah, 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 blah. Okay, good. Yeah, indeed, it is reduced. But I show you. So this is our first paper where we show the effect of the beam. Then the PhD student, Cameron Mezu, actually, he had a high resolution camera, online video monitoring. So here you see the cell, and here is this coppers going on. And again, that's the same spectra shows copper 2, copper 1, copper 0. So can we see that? I hope it will work here. So this is what you see. This is what happens in the cell with X-rays on. Now you would say, okay, I may never do X-ray experiments. That's not what I'm saying, because I just show it. I show this because it's such a quote, nice example, because from now on, I think every one of you will always remember this, hopefully, that this is an example. You can find several examples in the literature on it. Manganese is prone to it, vanadium, there's many of these elements are prone to it. And you have not to say that it is useless. That's not what I'm saying. What I'm saying is you have to look and be attentive that there is an effect. And you have to try to avoid and find ways to get it controlled. So what is happening here? So you have radiolysis, and it leads to splitting of the water. You will get gas formation, hence the bubbles. What you then have is copper is reduced from copper 2 to copper 1 to copper metal. You can analyze with electron microscopy, you'll find copper particles. Was interesting, or is interesting. Maybe if I have time next week, I will show you one in heterogeneous catalysis, because also there, these things can happen. Back to the cell. I show you this cell, and this cell can be used, and you can pressurize it. Many of you are maybe familiar with this cell, but many of you are also familiar with drifts, diffuse reflectance effect. I also have been using it since my PhD postdoc time. Now, I asked yesterday when I was at the Swiss Light Source if it still can be an issue. Here you have to be very careful. First of all, this cell has a dead volume point. Second, where is the thermocouple? Is it really positioned well? Is the temperature there for the right temperature? Question mark. I'm not saying it's not. It will be dependent on the flow rate you apply. Many things will control that. You have to double check it. That's my message. You have to be careful. And how can you do that? By making sure that what you observe corresponds, that you have not a peculiarity which is not found in a normal reactor setup. What is your gas Audi space velocity? Calculate or try to estimate, because I think you have to estimate it. It's not so straightforward actually to determine, because you have to determine what is this dead volume and whatever all, and how much gas is going through the system. But how can we measure now the temperature? How are we sure that we can measure it correctly? I've been, I will switch and show you something that I showed you before on Operando scanning transmission X-ray microscopy. Here you see the cell. Today, no fancy cobalt titanium spectra for explaining what the mechanism is. I just want to explain you why we came up with this cell, why we constructed the way it is. I told you, you have to have transmission. So that means your X-rays go through the catalyst and the gas atmosphere or the reaction environment. Yeah. So if you take 1 bar of CO at 250 degrees C, you can see here, if you have 2 plates, how far are they from each other? And you can still have transmission through the system. And you notice that you have to bring the cell to the 2 windows, which are actually silicon nitride windows in this case. If you want to measure carbon, you have to bring them about 50 micrometer apart. That's not a lot. And there you have to put your catalyst particle in. in between. If you do that, and there's a slide I showed you before in my previous talk, which I gave here at Zurich, this is the setup. You can measure titanium, cobalt, carbon, and whatever. But what you were not asking me, or you did actually not ask anything about it, is, yeah, but this is a spiral. And so here you see the spiral on the left bottom. You see a platinum spiral, and there in between these windows, there your catalyst particles are there. But where are they? Are they located in the middle, or are they farther apart? And how that then affects, because the gas comes from the left and go to the right. So actually there is something happening. So the first hints for that comes from this slide. We actually have, for those on online, particle 1, 2, 3, the red, blue, and green. There are 3 particles. And we measure here the same spectrum of these 3 particles while we want to reduce it. And in the middle one with the red orange, you see actually the 780 band. And when it goes up left, you actually have metal formation. And here you can see on the right what for these 3 particles, the 3 locations, how it is happening. And you can really, you don't have to be a specialist to say that it matters where it is. So it's not a uniform temperature. Sorry. So if you're doing your conclusion from the 1 versus the 3 or the 2, that means you will have a different conclusion made. True? How can you measure it? We developed actually, and credits have to go to also Andries Meijer, is a professor at Utrecht University who is specialized in luminescence. And he actually, with him, we have been working on, he's actually specialized in lanthanides, and you can have luminescence. You can make crystals who can, when you irradiate them, actually then you can have going farther, falling back, there are the green ones, and depending from what level it is, they give actually rise to 2 bands, which I call here in the figure I1 and I2. You can make a calibration line, and you can measure from the 2 levels the temperature. Okay, so what we did is we sprinkled these crystals into this cell. And now you can analyze 1, 2, 3. And what you can do is, here you see actually more of these particles, and we have defined them. In the middle, you see from A to J, you see different particles in different colors, and actually you have 3 zones: zone 1, zone 2, zone 3. 1 in the middle, 2 a little bit further, 3 in the surroundings. You already can anticipate what I'm there to tell them. So then you have, we set the temperature, and we do it in vacuum. And the center and the set temperature behaves rather well. You see the top right? It's not bad, but it's vacuum. Then you do air, and then you start to flow hydrogen or helium. And the message is here, you set the temperature, you will never reach the temperature you set locally. So you have to have actually a local sensor of the temperature, which could be such a crystal, to double check. And of course, after a while, because you know it, you know, if I'm able to put it somewhere in the middle, I have, for example, always 50 degrees offset. So I have to increase it to get the right temperature. I hope this opens your eyes. Maybe you knew it already, but I hope this also gives somehow a flavor that you cannot escape from it. Combining methods is very popular, as I already shown you before. Combining methods comes right away with another challenge, because it is already difficult to make a cell for one technique. What with another technique? True? But it's good to combine, because I showed you examples because you combine, you can check with one technique what the other technique is doing. True? So here is an example of once people have been using these optical fibers, the whole world was available. Here, EPR, a paper from Bruckner, then hunger, NMR, and you see a lot of these optical fibers which are connected. I have 3 statements to make here. Why? The same catalyst materials studied under identical reaction, providing complementary information. But are we always measuring at the same spot with the 2 techniques? I don't think so. So we have to make sample stability integrity evaluation by measuring the effect of one technique by the other technique. Show to you. Enhance that data analysis, making use of this combined technique approach. I think that is also valid. I will show you 2 cells from other people, and which we all also at Utrecht are using. And the second one actually is one which we modified. And here I refer to work from David Ferre at PSI, who designed a cell for doing X-rays combined with infrared. Some of you actually are using it. Those at least online, I'm sure, are using it. Here you see the cell on the left. And the whole point is that it has a low dead volume. And the advantage of this dead volume low means you can do transient type experimentation, because you can easily switch gases from A to B and back. And on the right, you see the cell, where you can, of course, have all the details, the X-rays in. And you see here on the left image, the orange beam or X-rays going in, and the top red infrared beam is going from the top in. Yesterday, I was at the Swiss Light Source. I actually had the chance to talk with the first author and also with the last author in this paper. And this is a nice example of where X-rays, because of the low dead volume, this is an ethanol oxidation. So what you have is you vary the level of oxygen while ethanol is constant. That means that you see that you have actually acetaldehyde, and you can have here the red, this going up and then here going down. And at the same time, you have beautiful spectra, as you can see on the right, where you can follow the dynamics of this vanadium, titanium, silica, if I remember well the system. This is an example where I think many people, including us, are using this kind of cell because it is, I'm not saying perfectly designed, but at least already well designed so that it mimics rather well also the catalytic data from a normal lab reactor. The second example, which also we are using, and I'm also fond of this one, it originates actually from the University of Cape Town in South Africa. And here they use a capillary. The capillary has an advantage that it is a capillary, so it has similarities to a normal reactor, provided you can make sure that the temperature is uniform. But if you choose the right flow rate or whatever, and also have good shielding of the reactor, then I think that is possible. These people have been using it for X-ray diffraction. Actually, it's also a commercial system to my best knowledge. Here you see it on the left. You can find more details in this paper, where you have this insulating capsule cover, X-rays in, X-rays out. And the most important is that also the thermocouple is rather positioned well, at least close to the bed. And so people have been using it, for example, because the group of Kleis is working a lot on Fischer-Tropsch, and it means that he follows, for example, cobalt systems. We have been using this system and added Raman to it. So here you see the cell on the bottom where you see this green, and here we actually have the laser coming in. By the way, we also can do it with UV-Vis, can actually add any method from the top. We did metal to hydrocarbons with UV-Vis, and with Raman we have been following the Fischer-Tropsch reaction. We did some modification. That is, I mentioned that you have to have also good relationship with people who build instrumentation. Actually, with this instrument, we have been working a lot. It's a Bruker D8 system, but we have been working, and we have a molybdenum radiation source, not copper, cobalt. So make sure that you have enough energy to get through. It means right away that you have, of course, other angles, but it is not a disadvantage here. You can actually have a bit more open. And what you can also have then is here you see that you can do this kind of things. It's very versatile. I'll just show you some examples on the left for X-ray diffraction, on the right for Raman. And it can be combined. I come back to my question. The question I want to ask to you is design a combined operando cell for your own work. And I invite you to send it to me before Monday, let's say noon, because I still want to introduce it. And I hope I can get 1 or 2 designs discussed here next week. So I really hope I can receive from you, based on your system, your suggestion, 2 techniques combined in 1 cell. And you have to make sure that it is properly designed in terms of temperature and whatever. So that I give you as an assignment for those who feel that they should get an assignment. How many minutes do you have? Or is it finished? Sir? 10. I would like to end my talk. It's okay or not? Oh, yeah, you don't dare to say no. Okay. I want to end with an example where I show you a journey since my PhD, and I don't show you actually the first few years, which was a dream. Can we bring this Operando ID up to the level of not an industrial reactor, but a pilot scale reactor? And those who follow our work, they know that we have been working a lot on light alkane dehydrogenation, as the chairman here is also working on light alkane dehydrogenation. We initially worked a lot on chrome alumina still, but it's now diverging to platinum, gallium, whatever else. This is a reactor in the Antwerp harbor, or near the Antwerp harbor, it's Callao actually, where you see the Houdry process, 5 reactors filled with a huge amount of chrome alumina catalyst powders. Years ago, I had already the idea, can we literally bring Operando approaches in a reactor? Why? Well, there are thermocouples and wells in a reactor. If you can bring thermocouples in a reactor, then you also should be, in principle, be able to put optical fibers in a reactor. No, it's not that different. So that idea, we want to pursue and see if we can measure in a reactor with Operando in an, I don't say industrial, but industrial-like system. So this is culminated in this paper, actually a ChemCat-Chem paper, where we published it, but it is a journey. It started first with praying mantis cell, diffuse reflects UV vis, then optical fiber, the left. And where we want to go is to really, what is shown in the right, where we develop not only temperature sensor, pressure sensor, sensing devices, where you can really measure inside the reactor. It started with taking a reactor, and here you see 4 optical fibers in a row. So you can measure, you have your catalyst bed. So the idea is, can you measure as function of the bed height? Think about this here. Here you see a bed. The bed is 1.5 meter, 1.5 meter in height. Can you then measure a function of the bed height? So that idea, we have been first starting at the lab scale, and the reactor itself was only a few centimeters. And you measured as a function of the bed height. But if you do that, you want to quantify, because what do you want to know? In this propane dehydrogenation reactor, or alkane dehydrogenation reactor in general, you form coke. coke deposits. And after a while, the active sites are covered by coke and you want to burn it off. So you want to measure the amount. How can you do that? Long story short, this is an equation, you have to believe me now, which you can correlate Raman and the darkening. If a catalyst gets black and black or less colorful, chromium 6 is yellowish orange, chromium 3 is green. So it means that you see a color change when it is actually darkening with coke deposits. What you notice, and on the left top, you see that actually the background is going up. Actually, the color is dark, the system is darkening, darkening. That one, you can measure, this is this reflectance. You pull that out. And these are the Raman spectra, and they are very peculiar. They go up and down. It would mean that you make more coke and then it disappears. Yeah, that's strange. That is an artifact because of the darkening. And you have to correlate that, compensate for that. And that can be done by taking the UV vis and actually take the reflectance and actually subtract is not the right word, but compensate for this reflection. That can be done by this formula. I show you here, we mixed it with boron nitride as a reference. And you see actually that the boron nitride, you see more and more that because of the coke deposit, you see less and less it appearing. So here I show you the quantification, the raw data going up and down, that makes no sense. And then the GR, that's this compensated version, actually you see it gradually builds up, and boron nitride, you see it also. It's not the same, but I would say that is reasonably. Most important is because you make a calibration line, you can put the amount of coke in weight percent. You can get a number on it. But that was the prelude. That was interesting, but now we go for the real stuff. This reactor is about 1 meter in size. Not yet one of the industrial, I assume, but I agree. I hope you forgive me that it's rather difficult to convince my university to build such a reactor in a lab. I think that is a bit too hard effort. But here you see it's about 1 meter, 77 centimeters. About. You see in the bed itself is about 50.5 meters in size. We also use not powders, but extradates, real life. So what I meant, what you now see is this is the real Operando mode. No powders, real stuff, the real catalyst. This is an industrial catalyst, put in a reactor, and then we have holes. We drilled holes in it. And these holes, you can put optical fiber technology. You think it's simple, it's not. Because the optical fiber has to withstand temperature and whatever all. And they have actually a collection mode and they bring light. Actually, you have 6 illuminating and 1 actually to collect it. You have to have a flow of helium or whatever to make sure that it is keeping the probe healthy. The second step was we introduced Raman. And here we also made a probe. And that was a real challenge. Making a Raman probe to withstand the conditions, to get it insert in a reactor is far from trivial. Okay, we managed. And here you see actually Ramon Oort putting it in the reactor. So we were able to measure UV vis, Raman, we correlated, we applied our formula. We have top of reactor spectra, bottom of reactor spectra, as you can see here, and they nicely increase. You see, well, nicely, you see the coke deposit band, the G and the D and G bands, as we call it in coke, increasing on the left. You can also measure the type of coke in the reactor, but that does not change a lot. So I hope with this example, there's one addition. And then you say, okay, Bert, fine, but can we do something else with it? Once you know the amount of coke, now you want that the reactor regenerate automatically based on your signal. Because you measure the amount of coke. When it reaches a certain value, then you say to the computer detects and says, regenerate. Is that possible? Otherwise, I would not say it then. I hope it will move. Sorry for those online, but I have this cursor, so hopefully you can see. So what is the green is actually the UV is correct. The red is the Raman correction. The raw data are in black. What you see is coke is built up, time is increasing, whop, we burn it off. And there's now a whole routine. You will see that there's an overshoot. You actually have to train the system, if I may say, to get the value right. So that you can just say, build up, regenerate, build up, regenerate, build up, regenerate. This is, in my opinion, an example where Operando, I'm not saying is a real industrial applied thing, that's not true. But you see how far you can push this kind of thing. It's towards applications in an industrial setting. So I hope with this tutorial, I showed you not just the fancy slides with all, but more what is behind. I showed you also the difficulties. And I want to end with some general comments. I hope I showed you that a realistic experimental setup, as well as catalyst material that mimics the catalytic process as best as possible is needed. If you can reach that level, I think we can learn really about the industrial or relevant process and learn all the intricacies. I hope you also have seen the acquisition of useful characterization data requires proper in situ Operando cell design, temperature effect, laser effect, whatever. Gas hourly space velocity also mentioned. Acquisition of complementary information, no single technique approach can be learning all what you want to know. And you think that combination of methods is essential. And last but not least, sample stability, integrity. Are we studying the catalyst? Are we studying something what is made due to your measuring method from the catalyst? And that is something you have to be careful. Next week, I have already stated that I will come back to some of your proposals on the cell design. So I really hope you will send me an email with your proposal. But I also will next week focus on, as a sneak preview, towards a molecular movie of a real-life catalyst that I will also show. With this, I wish you a very nice evening, but before, I have also to thank my group because they do the work. I'm just telling this. Thank you. Questions? Yeah.
So,
Just wait. We will bring a microphone to you.
So you mentioned a lot about this kind of the influence of the different techniques on the sample composition.
Yeah.
Now, is there, because I'm not too involved in this field, but is there like any kind of rules of thumb, like what kind of techniques can you combine, and why, for example, like do we always see this like only two techniques combined? Can you do more than two techniques?
I showed an example of more techniques. We saw and also always have been, there was actually at some point almost like a competition to have more techniques. I think up to 5 or 6 of them actually. I think 6 is now the record. But the whole point what I wanted to make with this image of this Operando dream machine is, at the end of the day, you still have to have the data to be combined on a system which is relevant, but that you don't have a system which only works for one catalytic system. I think you still want to build a setup not only for your PhD, but also for the follow-up PhD or postdoc or whatever. What you notice is that techniques which do not have a lot of energy are easy to be implemented, and I think that's very logical. But what are they done? I think you see a lot of infrared type things. Well, I will have to be infrared is heavily used in general, and people try to combine it with other methods. But the most easy to do is to use an optical window. So therefore, UV-Vis, Raman, or whatever is fluorescent, etc., is very easy to implement. The window determines a lot. Then, in my opinion, what you now also more and more see is X-rays go into the lab. I showed you this X-ray diffraction, but also X-ray absorption can be done more and more. So I think that a lot will come into the lab where you see SAS type applications with combined methodologies, because it becomes relatively easy to do that. And then you can, of course, not have the quality spectra as in the synchrotron, and that means the synchrotron have to rethink what their goal is, what they put on the table. And that will be then high quality, time resolved, whatever, space resolved methodologies, which are harder to be achieved in the lab environment.
And maybe also a question to your like kind of the end.
Yeah.
What kind of challenges do you expect when you go from this 1 meter reactor to like the big bottle?
I've discussed this topic several times with people in industry. First of all, that idea is actually an idea which I had already more than 20 years out. And it's so difficult to convince due to safety. Although it sounds trivial, but bringing in optical fiber technology where you're not yet sure about a potential leak or how long can it withstand, etc., how corrosive are the conditions. So I'm not saying people, there are examples where people are now trying and bringing it in. So I would be lying that there are applications in near infrared is a method which is popular, but Raman as well. However, in my context, people always have been a bit hesitant to get it implemented. Unfortunately, because I think this whole inline has a lot to offer. And yeah, I think that it's, you see it in other areas, you see that it works and can be used for process control. I think also here is something possible.
And now to that related, I'm always asking myself, is like what we are doing in the lab, it's all nice, but like is really like what's happening like in the big reactors, is that really the same what we are looking at in the lab? So
well, one of the big things is that in a large reactor you have a top and a bottom. In the top and the bottom in a lab environment, which is, let's say, 3 centimeters, then the difference between the top and the bottom will not be that much. But if you have a reactor which is, for example, 2 meter bed height, well, then it matters. Then the extrudate or whatever material on the top has seen a different gas composition compared to the bottom. And that means you have a different coking rate, a different whatever. And then it matters. And therefore, this kind of studies are of importance and needed actually as well. Because, I mean, engineers can of course calculate, so you can also reverse it. This can provide experimental input for models which chemical engineers have been making, process engineers. And I think that is where it, hopefully then, theory and experiment or modeling and experiment can come together. Yeah. Thank you. Other questions? Yeah. We'll just wait for the microphone.
Thanks for a great presentation. So a question about the Operando spectroscopy in the time domain.
Yeah.
So if you look at Raman, for example, Raman is a slow technique.
Yeah.
Do you think you can capture really the dynamics of, the reaction dynamics and the process dynamics that's required? And also, like, what are the techniques that you think will be are the best for let's say studying Operando in the time domain, real, let's say, dynamics.
With first, you have what I call measuring slow and long. Is very people. I mean, I agree with you, but I just want to also first to say people have to develop, or we have to develop methodologies which capture process for the long period. Let's be first putting that. I think that's needed. There, then all the methods can be applied because the time scale will not matter so much. And then on the short time scale, it depends on your process. If you have photocatalytic processes, for example, then your time scale is completely different and you will have to measure fast. Laser methodologies can be pulled or not and can be brought into fast regimes, femto, whatever, picofactor things. Referring to Raman, there you can also have that, for example, time-gated Raman is a way to get rid of fluorescence, actually, to make use of the time domain. You can suppress or get rid, artificially, if I may call it that way, of fluorescence, therefore boost the Raman, provided the signal is intense enough, and there starts Raman to be an issue. Fluorescence, on the other hand, is something what has a time domain, is rather intense, depending on how much molecules, but that is something would work. So I feel that everything what is laser pulse, light, UV, infrared, in that kind of thing, I think you have a lot of capabilities to make a time domain. But then third, last comment on this. People sometimes think that we have to measure for normal active site determination very fast. And there I disagree. Because the time scale of hundredths of a second should be sufficient to catch under dynamic or transient conditions in heterogeneous catalysis system what is going on. It's the turnover, you have to calculate turnover frequencies, turnover numbers. And then you start to realize that the number of turnovers is not that high. It's high because you have a lot of active sites. But per active site, it's not as overly fast process. Depends, of course, on the system. I have to be careful now. I define it back to this heterogeneous systems, although I step on toes of people. But I want to right away counter the argument that, so therefore I now push back to the idea of very fast, because that's not always needed. I think that many methods, when you bring them in 1/100th of a second, no, whatever, when you think of 1,000th of a second, you can do a lot. Yeah. But I hope you get the point. So you have very fast, I would say, normal condition, and then you have the real slow, and then all methods can go. Yeah. Other questions? Or in the chat. I don't know if there are people still online.
Besides EPR, is there any other technique to study radicals?
Yes. There are these fluorescent. Wait. Yes, there are methods where you're do laser-induced fluorescence of organic radicals. So, so yes, the answer is yes, but I'm not a specialist in it.
There's maybe a last question. If an institute technique does not involve fossilization, can we call it operando?
Sorry, this is an interesting one. Sorry.
So, if an institute method does not involve fossilization,
yeah,
can it be called operando?
Classically, operando was defined that we have to measure its online activity. But I forgot maybe to end my talk by saying, I hope you have seen that, in my view, 20 years later, we should maybe redefine a bit what this operando means, because the operando should really be that we talk about a system of relevance where we measure under the operating conditions. If we perturb the system for whatever reason, or not even close to the realistic conditions, then it can be perceived as operando, but not operando. So I think we should be a bit more careful. Online measurements does not guarantee you anything, because it can be that you just are measuring a site reaction due to beam damage or whatever. So you have to double check. It's not, I mean, I hope by showing this paper from 1969, where there was already in the two word an operando approach, that we should not be too fixated by the name. We should push our field forward, and the thing is, can we interrogate the catalyst system and learn something on reaction mechanisms, deactivation, active site? If that's the case, then we, as I showed you in one of these first pictures, I'm not saying rewriting the textbook, but at least checking and see if what is proposed on mechanism or whatever for certain reactions holds or it's not holding.
Okay, I think we can close the session. I will need to thank Bert again.
Yeah.
Don't forget your homework. Bert is waiting for cell design by Monday. Actually, Monday is Easter Monday, so I guess.
You can also send.
But I guess if you look very carefully in the eggs on Sunday, you may find a cell design within the egg. You know, Kinder also provides eggs with cell design. So, but anyway, so. Don't forget to send information. You can do that before the end of the week, and then Bert will be happy to discuss this. Okay, with that, all the best.
Thank you.
Thank you.